So, so you may, I mean, one of the reasons, okay, stack autoencoder gets its name is because you can train this autoencoder a stack at a time, okay? And this is called greedy layer-wise training, greedy layer-wise training. So this is especially useful, okay, when you do not have so many methods to fight with vanishing gradient. You know, remember in the old days, like training deep neural network is so difficult, okay? So they use this greedy layer-wise training to really achieve like training a deeper neural network, okay? Deeper autoencoder, I should say that, okay? So it's something like this, okay? So say this is your original input, okay? You only train this. So you can see that this is a very shallow autoencoder, right? So training this doesn't require a lot of training data, and it is more likely that you can you don't need to go through a lot of trouble, okay, to be able to train this model, because it's a shallow model, right? It's not so deep, right? Okay, so you don't need, for example, like you don't need a dropout. You don't need like a batch normalization. You don't need like a initialization strategy, or even like you know, if your you know, activation function is not ideal, okay, maybe you can still get this shallow autoencoder trend, right? Okay, and then okay, when you get, you know, try to, you know, I mean, this is original input, right? And I mean, try to preserve all the coding result of all your input. Why? Because we are going to use that to train another set of autoencoder like this. In this one, okay, the input is going to be the coding output of the original input. Okay? So this size is going to be exactly just like this. Okay? So this hidden one, in some sense, is going to be the input layer here. And you have another smaller, well, depending on your application, okay, you have another a layer like this, okay? And you have output layer, which again it's a shallow autoencoder, right? And this output layer size will be the same as this input, right? And you can train using not much training data, and again, because it's shallow, so you don't need to worry about like a vanishing gradient that much, you know. I mean, you know. So once you finish training, okay, you can copy the input. I mean, you can make a, you know, stack up these two autoencoder together to make a deeper autoencoder. So you copy the hidden layer from here, the weight of hidden layer from here. You copy this one to here. You copy this one to here, and you copy this one to here. Okay, so this is the way to train one autoencoder at a time, and you can stack up these separate different autoencoders together to form a deeper, more, you know, complicated autoencoder. Okay, this technique, okay, is called greedy layer-wise training. Okay, so you may ask, well, but when we are talking about this one, when we're talking about this, we just train this directly, right? we don't need to use this greedy layer-wise training. So why do we need to talk about this? Is this required? Let me put it this way. No. Okay, this is no longer required. Why? Because remember in chapter 11, we learned all those techniques to train a deep neural network, right? So we can train this model from scratch directly. Okay, this is no longer considered an impossible task, okay, nowadays. However, back to old days, like 1990, even like early 2000s, okay, to train a deep model is still a difficult task, okay? So they use this greedy layer-wise training, okay, to gradually stack up a deep neural network, okay, a deep autoencoder, okay. You may wonder, like, yeah, I mean, so why do we need to eventually create a deep autoencoder? The reason is that, remember, just like the application we just talked about, eventually we could use this part for transfer learning, right? We can use this part for transfer learning. Okay, and because training autoencoder does not require labeled data set, right? Okay, and we only need just a limited amount of labeled data set, okay, to do transfer learning from the encoder, okay, of the deep autoencoder, okay, but so, okay. I think I already explained, okay? So this one way to trigger the current tsunami of the interest in deep learning is a discovery of the 2006 by Geoffrey Hinton. So they use unsupervised pre-training, okay, to using the greedy-wise layer approach, okay. Of course, they use the restricted Boltzmann machine. Okay, so for the unsupervised pre-training, but Yoshua Bengio in 2007, they showed that autoencoders work just as well. Okay, just you don't need a restricted Boltzmann machine for to train a deep like autoencoder and then use that for transfer learning. No, you can use autoencoder. Okay. So, but nowadays it's not necessary because we learn so many good techniques from chapter 11. So we can just train a deep neural network, in one shot. Okay. But understanding this greedy layer-wise training is still a good idea because why? Because you can still see this technique being used in some, papers here and there. Okay, of course the paper may be like more than 10 years old, but when you do like literature survey, I mean sometimes you will encounter this type of stuff. So you need to understand what that listing is. Okay. So far the autoencoder that we have discussed are based on dense layers, right? Pretty much MLP, right? But obviously, you can use the same concept on convolutional neural network. Okay, you can use convolutional layer to create autoencoder, and you can even use the recurrent layer to create autoencoder. Okay, so let me show you. Okay. One of the convolutional autoencoder. Obviously, if your input is pictures, the convolutional layer process pictures much better than the dense layer, right? So, yeah. So this is an example. Okay, you see here. Okay, we directly treated as like you know, one channel, okay, 28 by 28 like input. So we use a convolution layer, conv2D, okay, with 16 feature maps, okay, and kernel size 3, padding same, elevation 0, and then we try to reduce the dimension by using max pooling, okay, with pool size 2, okay, and then we use another convolutional conv2D with 32 you know, feature maps, and well, same I mean kernel size 3 and same padding and 0 activation, and then again we reduce dimension by height and width by 2, okay, and then we have 64 you know, feature maps and you know, the same you know, arguments, and then we reduce the dimension further, okay, by 2, okay, on both width and height, and this is our encoder. Okay, but you may say like, well, how do we do the decoder part? Because the decoder, okay, when we, you know, in the CNN we normally shrink the input, you know, but but here, okay, we need to, in the decoder we need to enlarge it back, right? We need to enlarge it back to the original size. So what do we do? Okay, remember we have transpose convolutional layer. Okay, the transpose convolution, we talk about transpose convolutional layer in like you know, super resolution, right? We talk about that, right? We can enlarge the input by using the conv2D transpose. So you can see here we use a conv2D transpose. Okay, we now convert it to 32 feature maps, and kernel size 3, stride 2. Okay, this stride is actually, you know, 1/2, right? You know that, right? This basically means we stretch the feature map by 2 by size. I mean, we stretch the width and height by, I mean, double the width and height. Size, and padding is valid. Elevation 0, input shape is 3, 3, 64. Okay, 64 because we get it from here. Okay, and then okay, you know, because we have like this stride 2, so we enlarge it. Okay, and then we use the similar setting to enlarge it again, and then we cut the feature map by half as well. Okay, and then we cut it into one, well, and then, you know, stride 2. I mean, we enlarge it once more, and you know, now for each pixel we still use sigmoid. Okay, we still use sigmoid. Okay, this part is the same. We still treat each pixel as like a binary classification. Okay, and then we can combine this conv encoder and the conv decoder to form a conv autoencoder, convolutional autoencoder. Okay, so this one you can also train it, and you know, and it works well for the Fetch MNIST. You can obviously change this one to work with any you know, image input. Okay. Okay, so you can also create a recurrent autoencoder. Okay, so this is an example. Okay, so this one, okay, we actually treat each image. I mean, in the Fetch MNIST, okay, we treat it like a layer, you know, row by row. So we have 28, okay, rows. Okay, each row has 28 pixels. Okay, so you can see that. Okay, here we use the LSTM. Okay, with 100 neuron. Okay, and the output is sequential as well. Okay, and the input shape is non-28, That means like each input like we treat like is each row is 28. We just get any number of rows, okay? From the input, and then okay, this is our coding, okay? So we get like 30 neurons. This is for the coding. This part is our recurrent encoder. For recurrent decoder, okay, this keras.layers.repeat vector 28, input shape 30. That just means like we try to, at each time step, we just have this coding output these 30 values in order to create a sequence, okay, for the following recurrent layer, okay? So then we have a 100 neuron, okay, and return sequence to be true, okay? And then the last one, okay, again, we use time distributed chaos layer dense 28 elevation sigmoid, okay, and that's it. So you can combine these two to form a recurrent autoencoder. So now you see that we can create autoencoder using dense layer. We can use autoencoder. We can create autoencoder by convolutional layer. We can also create autoencoder by recurrent layer. Okay, so all this can be done. Okay. So I think I already explained this one. Okay. So far all the autoencoder that we have talked about, okay, are what we call under-complete autoencoder. There are other type of autoencoder called over-complete autoencoder. Okay, the under-complete autoencoder, as I said, most of the time is used for the dimensionality reduction. Okay, and remember we try to make autoencoder difficult in reconstruction in reconstructing the input, right? In the under-complete autoencoder, the coding layer dimension is already its difficulty in reconstructing the input, right? Because the dimension is lower than the input, so you have to find a good way to represent the input, right? But in over-complete autoencoder, that means the coding is not necessary. It's equal or greater than the input dimension. So obviously, in such a scenario, the difficulty part is not, okay, the difficulty of reconstructing the input doesn't come from the dimension of the coding, right? So we have to inject some other difficulties in order for this autoencoder to learn something. Okay, so there are actually many kinds of constraints that can be used. Okay, including one that allow the coding layer to be just as large as the input, or even larger, resulting in over-complete autoencoder. Okay, so for example, denoising autoencoder. Okay, this denoising autoencoder, okay, is like this. Okay. We force autoencoder to learn useful feature to add, okay, so we intentionally add noise to its input, okay, and we train it to recover the original noise-freed input, okay. So in the training, we add the noise by ourselves. So we still know what the original input is, okay? But we intentionally add the noise, okay? There are two type of noises we normally add. The first one is Gaussian noise, or what you can call like a white noise, okay? Which makes like you can inject this input, in the input, okay? The other one is like randomly dropped, randomly switch off input, this is also considered as one of the noise. Okay, basically it just means like at some point of time, like some input gets dropped. Okay, this can be mimicked by using the dropout. You can apply dropout on the input layer. Okay, so in terms of figure, it looks like this. Okay, if it's Gaussian noise, you just inject it here. This is your input. Okay, and you go through this autoencoder, and you try to train this autoencoder so that it can reconstruct the input. Okay, and this input will be as close to this one without the Gaussian noise. Okay, you train it. When you train it, you try to do this, and after you finish training, you no longer add the Gaussian noise. Okay, you no longer add the Gaussian noise. The input will already contain the noise, and your autoencoder will be able to remove those white noise from the background for you, and to output like the noise-free result. Okay, and for the rendering switch of like noise, I mean, you just try to add a dropout layer on the input. Okay, to randomly switch off certain input. Okay, during training again. After training, we know dropout, I mean, doesn't work after, I mean, when we do the inference, right? So this layer is like automatically disappear. Okay, I mean, after training. So I mean, we can use this autoencoder to sort of like reconstruct or like fill in the missing values. Okay, or you can call it imputation. Remember in the previous slides, I told you there are two things. Okay, I mean the forecast and the imputation. Okay, I mean in the RNN part. Okay, and so this is perhaps the first model in this class I talked about. Like we can impute the data. Okay, so here is like one of the example. Okay, of the denoising autoencoder, and here we use randomly switch of input noise. So this one work with like the fashion MNIST. So you can see that here. Okay, we have the flattened input. Okay, and we apply the dropout. Okay, the dropout rate is 0.5. So half of the inputs will be turned off. Okay, at random, right? Because the dropout rate is 0.5. Okay, so and then we have like a dense layer of 100 neuron, zero activation, 30 neuron. Okay, and zero activation again. So this is a coding layer, and so that's the encoder. For the decoder, we have 100 neurons. Okay, for the first layer with zero activation, and we also get input from the coding layer, so it's 30. Input shape is 30, and then we convert it back to 28 by 28 with sigmoid activation, and then we have to reshape it back to two-dimensional. Okay, and then you can combine this dropout encoder and the dropout decoder together to be a dropout autoencoder. So this one, because of this dropout layer, during training, half of the input, will be turned off at random. Okay, so but this autoencoder is going to learn to reconstruct the missing values, and yeah, this is well, even though I say like denoising autoencoder doesn't need to be under complete, but this example happened to be also still under complete autoencoder because the coding layer dimension is much lower than the 28 by 28, right? But I mean, this doesn't have to be 30, okay? If you want this to work even better, you can change this value to become like maybe like a 700 something, okay? Just like the input size. But anyway, okay, so if you try to draw the result, okay, you can see this is actually the input after dropping out 50% of the input. So if you don't see the lower row, can you tell what they are by looking at this input? The only thing you can probably tell is maybe, oh, this one looks like a t-shirt. This one looks like a long sleeve. This one looks like a shoes, right? Okay, like it looks like high heel, okay? But, for these two, it's probably difficult to tell. Okay, but the reconstruction is very reasonable, right? The reconstruction is very reasonable. Okay, so this tell you, okay, you can use autoencoder to fill out the missing values. Okay, even when the missing value, okay, you have 50% of the missing value. I mean, you can still, the autoencoder can still, find a way to do a good job for you. Okay. So now, okay, we talk about like already finished another application of autoencoder, which is like get rid of noise, either the white noise or like doing the imputation for us. Okay, and the next one is called a sparse autoencoder. What is sparse autoencoder? Okay, sparse autoencoder is trying to do feature extraction. Okay, we try to make the coding layer, okay, to activate as little as possible, and by enforcing the coding layer to react as little as possible, okay, or enforces what we call sparsity, okay, then the coding layer is going to kind of represent like important features. Okay, each dimension is going to represent like one important feature. Yes.
So in the coding layer, not every neuron is active. That's normal.
Yeah, of course. But now we want it to react even lower than that. Okay, I will tell you. I mean, what we are doing here. Okay, give me. Let's finish this one. If you have more questions, you can ask. Okay, so for example, it may be we may push like the coding layer to to have average only 5% active neurons in the coding layer. Only 5%. That's much lower, right? Much lower. Normally, like the coding layer. I'm not saying coding layer has to be like active all the time, or I mean all of them have to be active all the time. But at least like the coding layer, like normally we don't put the restriction for the coding layer to activate. Okay, but now like we intentionally make the coding layer to only react or to activate only 5%. Okay, something like that, in order to enforce this sparsity. Okay, so you may ask, so why does this become a good feature extraction? Okay, I mean it's just like if I give an example. Okay, if I put a restriction on you, say like you can only speak like a few words per month. Okay, then I mean you would probably just say some very meaningful words, right? Every time you open your mouth, the words you spit out must be very meaningful, because I put this restriction on you, right? So this is like exactly just like this, okay? I mean, for the autoencoder as well, okay? So how do we put the restriction on the coding layer? Okay, one way to do it is, remember you guys have learned the L1, right? Okay, so you can see for this one, okay, we call it sparse L1 encoder. So I mean the other part is the same, okay, as like the previous one. The only difference is that here, okay. Oh, by the way, this is the over-complete autoencoder. So you can see this, the coding layer, the dense layers, is 300 neurons. It's well, it's still not as big as the input, but it's a lot bigger, right? So 300 activation sigmoid, and see we put additional layer called activity regularization, L1 equal to 10 to the power of -3. So this is a very small value. This is a very small value, and the other part remains the same. Okay, and we combine this sparse L1 encoder and the sparse L1 decoder to form our sparse L1 autoencoder. So when you train this neural network, this autoencoder, okay, your coding layer will not react like so frequently because, you know, we actually try to, you know, make sure like the activation, okay, or I mean its output, okay, the L1 value of this layer, okay, is going to be lower than 10 to the power of -3, okay. So so this is like you know one way to enforce this sparsity, okay, and so using the L1 norm rather than the L2 norm, okay, will push neural network to preserve the most important codings, because we know L1, okay, when you use L1, it will only leave like a few neural network to be non-zero, okay, and the other they'll push the other to be zero. But if you use L2, they'll push all the neural network, all the neurons to output small values, but they will. I mean, it will not, you know, eliminate the output of like the other neurons. Okay, so normally we use L1. Okay, but so this is like just one way. Okay, but this normally doesn't perform very well. Why is that? Okay. What should I say? Okay, it's like this. Okay, when we want the sparsity, okay, it's like we want, say like okay, if this class is an autoencoder, say this line is the coding. Okay, it's a coding layer. So we have three neurons. So when I put these restrictions, okay, by using this L1 regularization, I mean, I only restrict like the sum of these three neurons, right? But sometimes I want to enforce. What I want to enforce is like, okay, say like I want like the neurons, each neuron in the coding layer to only activate like maybe 10% of the time. Be very careful. Here I want each neuron, so you react 10% of the time, you react 10% of the time, and then the third one react only 10% of the time. So it's not like the sum of you guys. I want to enforce like you know, each neuron in the coding layer separately. Okay. So this is also sparsity constraint, but the you can say the resolution of such constraint is even much stronger, right? It put a much more stronger constraint on every neuron, okay, instead of just a group of neurons. Okay, so how can we achieve that? Okay, to measure the actual sparsity of the coding layer at each training iteration for each neuron, and parallelize the model when the measured sparsity differs from the target sparsity. Okay, we do so by computing the average activation of each neuron in the coding layer over the whole training batch. So first, I mean, obviously, if you want to do that, the batch size has to be big enough. If the batch size is too small, then I say, 10% of it, I mean, because this 10% is computed based on one batch, right? So that 10%, if each batch you only have like a very few instances, then it's probably not going to, the calculation of 10% is not going to be very accurate, right? So the batch has to be, at least not too small. Otherwise, the mean will not be accurate, okay? So once we have the mean activation per neuron, okay, so this is enforced per neuron, okay? So we want to penalize the neurons, okay? But, that are either too active or not active enough, okay? In L1, we only penalize, if the group of neurons active too much, right? But if the group of neurons doesn't active that much, we doesn't penalize it, right? So this one is much, put a lot like granularity of, in terms of restriction on the coding, the neuron in the coding layers. Okay, so for example, if we measure a neuron has average activation of 0.3, like 30%, but the target sparsity is 10%, then it must be penalized. Okay, but if this neuron, the activation is 0.05, only 5%, and the target sparsity is 10%, that neuron will also be penalized. Okay, it's not just like when this neuron activates too much. When this neuron doesn't activate at all, we also penalize that. Okay, so we have this target sparsity that we want every neuron to achieve at least as close as possible. Okay, this is very different from the previous approach. Okay, so one way is to add the square error, okay, like to the cost function, right? But in practice, okay, we normally use like what we call KL divergence. Okay, the fullness callback library. This is like my pronunciation may not be accurate because this is these two guys. This is the name of two guys, but they are Germany. Okay, so I'm not sure if my pronunciation is correct, but the abbreviation is called KL divergence. This KL divergence, okay, is a famous mathematical tools to measure the how far away two distributions are from each other. Okay, so it quantifies how far two distributions are from each other. Okay, if two distributions are exactly the same, the KL divergence result is 0. Okay, you get the idea. Okay, so basically, okay, I will not go into the detail. Okay, how to derive this KL divergence, but chapter 4 talk about this, but we didn't talk about chapter 4 anyway. Okay, but it has much stronger gradients than the mean squared error. So that is why, okay, when we use this for training, okay, we get more gradient, okay, that help us to train this model much faster. Okay, so here just to show you, what the KL divergence value looks like. So you can see, okay, so if it's MAE is like a mean absolute error, so it's like just like linear, right? The error is just linear, but MSE is a square root error. So it's this red line, but the KL divergence is represented by the blue line, And you can obviously see that this blue line has a much stronger gradient than the other arrow function, right? So that's why, okay, you can, we prefer to use KO divergence here. And this is how we construct, compute the KO divergence, okay? Because we are talking about discrete probability distribution, okay? So the calculation is like this. And here, in our application, because it's even easier, okay? It's not exactly a distribution. It's just like the probability of the activation, right? Okay, it's just one value, right? Just one value, okay? Maybe, the target sparsity is 0.1, that means 10%, right? Okay, 10%, that's our distribution, right? Okay, just represented by a value P. And so if our target probability is P and the current activation is Q, then the KO divergence computation can be converted to something like this. Okay? So then, okay, there's another hyperparameter called sparsity weight. Okay? Because think about this. Now you have a cost function. The cost function is constructed by two parts. The first part is like a reconstruction loss, right? Reconstruction loss basically penalize the model when the autoencoder doesn't reconstruct the input well, right? That's a reconstruction loss. The other one is this, sparsity loss, right? Sparsity loss. You can imagine, okay, when you set this sparsity to only 10%, okay, this is obviously a constraint for the coding layer, right? Okay, and when you put the constraint for the coding layer, it makes the reconstruction more difficult, right? It makes the reconstruction more difficult. So these two cost terms are somehow like what should I say, like have different purposes, and these two different purposes are kind of fighting against each other, right? Because, well, if you want the reconstruction to be as successful as possible, you shouldn't put any restriction on you shouldn't put any constraint on the coding layer activation, right? Okay, but on the other hand, if you put a coding layer constraint, activation constraint, then the reconstruction will be constrained, so it will not perform very well, right? So for these two terms, okay, so we have this sparsity weight. This sparsity weight is multiplied to the sparsity loss, okay, and if this value is bigger, it means you care about this sparsity constraint more, and you do not care reconstruction loss that much. If this sparsity weight is small, that means you care about this reconstruction more, and you doesn't care that constraint that much. Okay? Just want you to be to have an idea what this sparsity weight. But in general, this sparsity weight is like value is in between 0 and 1, and you don't need to set a large value for this. Maybe set a 0.1 or even lower than 0.1. Normally can get you to a very good result already. Okay, so here, okay, so here we want to implement this sparse autoencoder. Okay, so first we create a custom regularizer to apply the KO divergence regularization. So this one is like the KO divergence is just like this is just we can call this callback library divergence. Okay, from we just get the loss from here. Okay, and then okay, here, okay, it's just like we just define this. This is like we compute the KO divergence by using the target, okay, and the mean activation, so this part is actually just like exactly this one, okay. So you finish this one, and then you multiply this to the weight. This weight is the sparsity weight hyperparameter that you get from. I think we get it from the parameter, I mean input parameter. Okay. So anyway, so once you have this, you know, this loss, okay, like a KO divergence law. Loss. Ready. Okay. Oh, sorry. KO divergence regularizer ready. Then, okay, here, okay, we first create an object of this, and we specify the KO divergence. The sparsity loss is weight is 0.05. Target. This is the target activation is 10%, 0.1. Okay, and then here, okay, you see again this is fashion MNIST. So you have like input shape 28 by 28, and then 100 neuron zero, so 300 and sigmoid activation. So we set activity regularizer to be this KLD reg, okay, that we already created there, okay, and then in the decoder it remains the same, and then we combine this encoder and decoder to form our sparse KLAE, and if you train this model, okay, and you, when you see how it reacts to your data set, you will find that, okay, for example, here, okay, actually 90%, okay, of the percentage of activation, okay, for the neuron have the percentage of activation like within like 0.1 to, lower than 0.2. Okay, average, I think the average is like 1.1. Okay, 1.1. And this one just means like neuron mean activation. And you can see, most of them, their average is like 0.1. Okay, so this is to just show you, okay, this the sparsity autoencoder is doing a very good job. So each neuron will actually represent different meaning, okay, in the coding layer, basically. Okay, when that one is activated, you can imagine, okay, the input must mean certain something. Okay, so you can sort of like explain that using the features represented by the neurons in the coding layer. Okay, so sorry to take you a little bit more time. So let's take a 10 minutes break. When we come back, okay, we are going to talk about the last subject of the autoencoder. Okay.